Good morning, physical science students. We are wrapping up Unit 5A on matter with this last video lesson on gas laws. So this is our fifth video lesson in this unit. We are today talking about how temperature, pressure, and volume, in addition to density, relate to gases in a closed system. So starting with just some basic information about gases. So when we talk about gas, we frequently have to talk about pressure. And pressure for gases is the result of a force over the area. So when you have like a balloon, for example, you've got more pressure inside the balloon than you do outside the balloon. That's what allows the balloon to expand. In the balloon, you've got air particles flying around and they're hitting the wall of the balloon. That is what we are talking about when we're talking about pressure. It is force over an area. Pressure is produced by a gas with the particles colliding with the wall or the side of the container. Now, the collisions between the particles of gas and the walls of the container cause the pressure in a closed system of the gas. We can do other things within that closed system to change the temperature or change the volume of the gas. But the pressure that we are detecting is due to how much or how many collisions those particles have with the wall of the container. The more frequent the collisions, the greater the pressure of the gas. So the more they collide with the wall of the container, the higher the pressure is going to be. Now, there are three things that affect the pressure of a gas. First is temperature, second is volume, and third is the number of particles. Changing any one of those three will have an impact on the pressure. So temperature, if we change the temperature of a closed system, so I've got a box with a gas in it, or a bottle, can, whatever, with a gas in it. If I change the temperature, it's going to increase the kinetic energy of the particles. The particles are going to start moving faster. If they're moving faster, they're going to hit the wall of the container more frequently. The increase in the number of collisions is going to result in an increase in the pressure. So in terms of the relationship between pressure and temperature, if my temperature increases, my pressure will increase. If you've ever seen like a can of hairspray thrown into fire, you'll notice that it explodes. The reason it explodes is because the pressure gets so high, because the temperature is so hot, that the container can no longer contain that amount of pressure. This is called a direct relationship. So they are directly related, or it's also called proportional. I don't think I spelled proportional right, but that's okay. All that means is if one goes up, the other one goes up. Reverse is also the true. If I decrease the temperature, the pressure is going to also decrease. You can see this by, sorry, how to think. When you cool something down that is a vapor, the particles are going to start moving slower. They might turn into a liquid if you get it cool enough, but they're moving slower, therefore they're going to hit the walls less frequently. So the second thing that can affect the pressure of the gas is the volume. This is assuming that we have a container that we can control the volume on. So picture a like steel container with a lid that can go up or down. By reducing the volume, if we decrease the volume, the pressure will increase. It is an opposite relationship. They are inversely related. So if my volume is getting smaller, I'm making my container smaller, smaller, and smaller, the pressure is going to keep going up. Opposite's true. If I make my container larger, I give more space for the particles to flow around, the particles are going to hit the wall less frequently, therefore the pressure will decrease. That is an inverse relationship. Sorry, I can't talk. The third thing that affects the pressure of a gas is the number of particles. Think of this as the amount of gas in the container. The more particles that you have in the container, the more times particles are going to hit the side of the container. Again, assuming a rigid container. If I push more gas into that container, if I increase the number of particles, then my pressure will also increase. Opposite again, true. If I take some particles out of my rigid container, the pressure inside that container will decrease. This is a direct or a proportional relationship. When one goes up, the other one goes up. So adding more gas will increase the pressure. Losing some of the gas from the container will decrease the pressure. Now, these relationships that we've mentioned connect to 3 gas laws. There are 3 different scientists over the years who have done experimentations with gases and have established 3 specific laws, each one dealing with pressure, temperature, or volume. So our first law is Charles's law, and Charles has the pressure. What that means is Charles always holds pressure constant. That means he doesn't change the pressure. So Charles changes the other 2 things. He tells us how temperature and volume of a gas are related. So if I take a container that is flexible like a balloon and I put a gas in it and I cool it down, you would see this possibly a winter morning, early cold fall morning. Blow up a balloon inside, take that balloon outside, the volume of the balloon is going to shrink some. The colder it is outside, the more it's going to shrink. So put it in the freezer, it's going to shrink a whole lot. The volume and the temperature, as my temperature decreased, my volume decreased. That's a direct relationship. Same idea. If I take my balloon and I go and put it in something hot, like if I were to put it in a warm house or a hot water bath, then the volume of the balloon is going to get larger. So if the temperature increases, it's going to push on the side of the container more, and since it's a flexible container, the volume will also increase. Now, Charles holds pressure constant. Charles has the pressure. His law talks about the relationship between the other 2 things. They are directly proportional. When one goes up, the other one goes up. When one goes down, the other one goes down. Our second law is Boyle's law. Boyle's, think a little bit like boil, B-O-I-L, and Boyle's law holds temperature constant. So Boyle's law, he doesn't talk about temperature. His law talks about pressure and volume. And it tells us that according to Boyle's law, pressure and volume are inversely proportional. That means if the pressure goes up, I increase my pressure, that means my volume is going to decrease. Or if my volume increased, that means I had to decrease the pressure. It is the opposite relationship. So this time we're assuming that we have a rigid container and we're able to change the volume of the container. So if the volume is larger, these particles are going to hit the walls less often because there's more space. If the volume is smaller, they're going to hit the wall more often, hence the increase in pressure. And last but not least, our third law, Gay-Lussac's law. Gay-Lussac's law doesn't talk about volume. So Gay-Lussac's law does not deal with the V. His law deals with the other 2 things, the T and the P. So his is talking about the relationship between temperature and pressure. We mentioned this earlier. If I increase the temperature, we are going to increase the pressure. The reason for that is particles at a higher temperature move faster. they're moving faster, they're going to hit the wall more frequently, which means we're going to have an increase in pressure. So, generally, Gay's law, or Gay-Lussac's law, sorry, if the temperature increases, the pressure will increase. Now, the nice thing about these three gas laws is because the number of particles are constant, there is a nice little manipulative that you can make that allows you to actually see the relationship between these gas laws. And I just realized that my choice of color makes it very hard to see in the video, so let's see if gray is a little bit better. Probably not. Okay, a little bit easier. So, if you take just a normal piece of paper or an index card, and along the side put the letters in order P, T, V for pressure, temperature, and volume, it will tell you whose law holds what constant, and you can actually see the relationship for each of these. So, for example, Boyle's law holds temperature constant. So I'm going to hold my T. Notice that if I pull the V up, what happens to the P? Sorry, I pull P down. Notice what happens to the V. So I'm holding my temperature. I pull P down. I can see that the volume is going up. Pressure is coming down. Volume is increasing. That is that opposite relationship. It works the same way. I'm holding temperature. I pull the volume down, pull the V down. Notice pressure has no choice but to go up. Right. So that was if temperature was held constant. Let's look at what happens if we hold pressure constant. So if I hold pressure constant, pressure, Charles has the pressure, he holds pressure constant. Notice what happens if I pull temperature up, volume goes up with it. If I push volume down, temperature goes down with it. They are directly proportional. They both go in the same direction. Last but not least, Gay-Lussac's law. Gay-Lussac's law, his law doesn't talk about the V. His law does not talk about volume. So his law, we notice that if temperature increases, notice the pressure increases. I'm holding volume constant. I'm not letting it move. If my volume decreases, that means the temperature had to decrease as well. Again, they are both directly proportional. This is a great manipulative to have out when you're trying to answer gas law questions, as well as just adding under each of those letters, like I have on the screen, the scientist's name, and their name is telling us under what they do not talk about. So their laws talk about the other two things. So some real life examples of gas laws. Don't know if you guys have had the opportunity to see the hot air balloon that likes to wander around the Ola area. But if you've ever been on one, in order to make a hot air balloon rise, they have to put hot air in the balloon. Well, air that's been heated is less dense. That is because the particles have spread out due to the increase in temperature. They spread out, they're increasing their volume because the temperature is increasing. By adding the heat, it causes the molecules to move farther away from each other, and it allows the balloon to rise. This is, by definition, Charles's law. Charles's law has the pressure. This law is talking about pressure being held constant. With the balloon, it's atmospheric pressure, but his law talks about temperature and volume. Another example, this would be Gay-Lussac's law. The air in your tires or your parents' car tires, the pressure of that air actually increases over long trips. So as you are driving the car, the pressure inside your tires are going to increase. The reason why the pressure is increasing is because the air in the tires is heating up. The tires are going along on the ground, they're experiencing some rolling friction that heats up the tires, which heats up the air. Well, the air is contained, the volume is constant. Gay-Lussac's law doesn't talk about the V. So his is volume's constant. So Gay-Lussac talks about what happens with pressure and temperature. So if the temperature goes up, pressure goes up. The pressure in the tires can get so much, if they get too hot, that it can actually cause the tire to explode. It's another reason why on cold mornings, the tires seem to be a little bit slack early in the day if you have to, park outside. It's because the particles aren't moving as fast. Therefore, the volume of the tire is going to decrease just a little bit. Last real life example, this is Boyle's law. Boyle's law, his doesn't talk about temperature. We think about boiling. So his law is talking about pressure and volume. This is an example of soda. So when they are making bottled soda, in order to get the carbonation in there, which is just carbon dioxide, but in order to get the carbonation in there, they have to put a lot of pressure on that bottle. They are pushing in gas into that liquid. They're increasing the pressure. This is the reason why you open the bottle and you kind of hear that hiss, because it's under pressure. Some of the particles are going to escape. Thinking about if you're trying to squeeze a bottle that's never been opened, they don't really compress much. And that's because there's no room to really push those particles any closer. They have kind of had the most amount of liquids and gases that they can. So if we, of course, change the number of particles, we're going to change the pressure. But pressure and volume, increasing the pressure, means my volume is going to go down. If my volume is going up, that means I'm having to decrease the pressure. If we let the pressure off the gas, it's going to fill up the air. Or the bottle, it's going to fill up the air in the room. If we put pressure on the gas, we're condensing it down into a smaller space. Lord, I cannot talk. Another real life example of Charles's law, turkey thermometers. That looks really funky, but sometimes you can buy turkey that already have those thermometers in there that will pop up when the turkey is done. And the reason why it pops up is because there's a little bit of air in there. And when that air gets to a certain temperature, as it's heating up, the volume is expanding just a little bit as it goes. Well, once that volume reaches a certain amount, the little red thing we see on the screen pops up, indicating that the temperature inside that turkey has reached that specific temperature. And therefore, it is safe to take the turkey out of the oven. It's cooked enough. The reason we know this is because the volume of the air is proportional to the temperature. If we increase temperature, the volume will increase. And that was my last example for some real life things with our gas laws. As always, make certain you complete your practice that is in Google Classroom. If you've got any questions, feel free to send me messages or pop in my open office hours. But that is it for this particular video lesson.